بسم الله الرحمن الرحيم. Gas laws, molecular theory. In solid, the atoms or molecules are usually arranged in a form called lattice. Whenever heat is applied to the solid, is being broken down to liquid. The force of attraction of the molecules are called van der Waals forces, which can be broken out to form gas or vapor. Gas laws are three in form. First of all is the Boyle's law, which correlates pressure to volume at a constant temperature. We have two syringes, as we can see. Whenever I make the temperature constant, of course, definitely the pressure will decrease whenever it is increased. The clinic application of it is the 10 liters of oxygen cylinder, where the pressure is 13,800. Whenever I multiply by the volume of the cylinder, it can yield how much of the oxygen this cylinder is contained whenever it's being released at the atmospheric pressure. Of course, V1 equals the multiplication of P2 and V2 and so forth. The second law is the Charles-Auger-Lussac law, which correlates the pressure to the constant. Is directly proportional, as you can see, and this is whenever they are figured out by an equation in which the K2 is the second constant. The clinical application is not much important. Whenever the gas is being heated, it becomes less dense. The third gas flow we call it the third perfect gas flow. Most of the gases they cannot fulfill much of the laws apart from hydrogen molecule. So it correlates the pressure to the temperature whenever the volume is constant. The clinical application of it is the hydrogen thermometer, which is being used to measure temperature where the volume is the pressure is correlated to the temperature whenever the volume is constant. Another thing is that the cylinder is made to withstand the pressure of 200 bar, because of course heat can increase much to make the cylinder explode. Adiabatic exchange of the state of gases, all of what happened before in the gas, it's correlated to the application of heat, but the molecular kinetic energy of the molecules can induce changes. For instance, if I fill a cylinder by gas or oxygen, suppose forcibly, the movements of the kinetic energy will increase and the heat will increase, needing a cooling system. In other words, also, whenever I empty a cylinder or open an anesthetic machine, this gush of gases coming out will increase the temperature, needing a method of cooling. On the other hand, whenever this gas is being compressed and released from a very thin tube as the cryo probe, the attraction of van der Waals are being broken down, leading to severe decrease in temperature, as you can see in the nitrous oxide cylinder, up to -70, which is used in cryosurgery and alleviating pain after thoracotomy. This distracts the nerve sheaths, and it's been returned within 6 months. Dalton's law of partial pressure, it correlates the pressure of the mixture of gases. It denotes that whenever the mixture of gases are with each other, whenever it's being released in one of a cylinder, it exerts the same pressure that it was present in the mixture of cylinders. Clinical application, we have 3 of them. First of all, the Intenox cylinder, where the oxygen and nitric oxide are present 50-50 as a concentration, and the pressure is 100 kilopascal. If we take each of them, which is 50%, and being put in a separate cylinder, each of them will exert the same pressure, so they will work in a high volume. But instead of being a pressure of 100, each of them will create a pressure of 50. Of course, knowing the pressure, among all the pressure, we can utilize it by using Dalton's law to know the concentration of any gas in any mixture. The second is the air cylinder, where we have almost oxygen in around 90 point something 90%, and nitrogen in a cylinder of 100. Of course, each of them exerts the pressure according to its concentration. And whenever I release each of them in a separate cylinder, it will exert the same pressure, and we can also yield the percent of the gas in this mixture. The third application is whenever I want to fill a cylinder by oxygen and carbon dioxide. First of all, I induce suppose I want 10% carbon dioxide. I admit the carbon dioxide till the pressure is 10% of the total, which is 183. So whenever it reaches 13.8, I stop, and then I continue with oxygen. These are the figures. Of course, whenever I have water vapor in a mixture of gas, I ought to remove it from the total pressure. As you can see, 100 and point. This is the standard pressure minus 6.3, which is the pressure in millimeter mercury pressure of water vapor, and then I multiply. Suppose if I want the carbon dioxide, I multiply by the concentration of carbon dioxide, which is 5.6 over 100, and will yield the PaCO2 without water vapor. Avogadro's hypothesis states that whenever I have equal volume of gases, whether they are nitric oxide or carbon, whatever, equal volume of gases at the same temperature, not standard temperature or pressure, has the same volume. You see, this volume or molecules are different in their mass, but at the end result, both of them in the same temperature will have the same volume. One volume of any gas as a standard. I will tell you later on what's the meaning of a mole. 1 mole of any gas, a standard temperature pressure, occupies 6.022 times 10 to the power of 23. So you ought to memorize this figure. The mole is an expression of the mass or the quantity of a substance, where 1 mole of any gas or any substance contains the same number of the particles. As we can see, this Avogadro's number, as you can see. And this is a way where we introduce carbon 12, and this carbon 12 contains the number of particles present any 1 mole of any other substance. This is the meaning of a mole. Clinical application of a mole is how to standardize a vaporizer, calibrate a vaporizer. Suppose we have an isoflurane, as we know, an inhalation anesthetic, which has a molecular weight of 184.5. This is the molecular weight. So whenever I want to get 1 mole, I get 140 and 84.5 gram of isoflurane, creating 1 mole. This mole occupies, as we said before, 22.4 liter at standard temperature or pressure. So if we get a 0.1 mole of isoflurane, it will occupy only 2.24. You see, so what is the constant or the required flow that goes to the vaporizer to create a 1%? Simply speaking, if I want to get 1%, I ought to divide 224 liter by the amount of liter coming out from the vaporizer to create the 1%. Of course, this value is different because it is the vaporizer is being used in non-standard temperature and pressure, and of course, as we know, most of the gases do not obey perfectly the gas law. If we have also an nitric oxide cylinder where it contains 3.4 kilogram of nitric oxide. And of course, you can figure, if you know that the molecular weight of nitric oxide is 44, you can figure out how much this 3.4 kilograms contains of moles, and each mole, as we know, contains or occupies 22.4. So whenever I figure it out, I'll find that the cylinder can yield around 1,730 liters. So these are the figures you must memorize. Of course, the 1,380 of oxygen, and this one of nitrous oxide. So this is the Avogadro's hypothesis and the Avogadro's number. Universal gas law, whenever I control or I gain the three gas law with each other, put them with each other, I can reach that the PV over T equals constant. Whenever I add the number of molecules according to Avogadro's hypothesis, I gain this final equation where PV equals nRT. So whenever the volume, suppose, of oxygen cylinder is constant and the temperature is constant, the pressure of the cylinder definitely will correlate to the number of molecules. This is why we call the pressure gauge acts as the content gauge. This means that the oxygen cylinder, the pressure gauge on it, it gives a hint about the amount of oxygen present in it. Critical temperature. Critical temperature, as we said before, is a temperature where the gas can be transferred to its liquid, but it's defined as the temperature above which never you cannot change the gas to liquid if the temperature is not reached off. So it's defined as the temperature above which a substance cannot be liquefied, whatever much pressure is applied. Of course, of oxygen is well known, that's minus 119 degrees Celsius. And in nitric oxide is 36.4 degrees. So these are the critical temperature you ought to remember. What's the critical pressure? Is the pressure at its critical temperature. So whenever I fill nitric oxide and oxygen at the same time at the temperature of 20, we'll find that at the time whenever I'm filling the nitric oxide, this nitric oxide at this temperature will be transferred to a liquid, and the pressure of the gauge of the cylinder will not give a hint about the total amount, because the liquid is being present with the gas. On the other hand, the oxygen is, whenever it's always the gas, the gauge indicates the amount of gas present in it. Pseudo critical temperature is another method to denote what's the meaning of the critical temperature whenever I have a mixture of gas. Suppose we have nitric oxide oxygen 50-50, which is present in cylinders to elevate pain. This is made possible whenever they are both in the gaseous state. So we ought not to diminish the temperature beyond minus 5.5 degree. Otherwise, nitric oxide will be transferred to liquid and will deliver an hypoxic level of oxygen. So this is why we ought to keep the cylinder in a transverse position and keep it in the optimum temperature. Filling ratio is a ratio where we guard against the excessive filling of a cylinder, where, of course, never forget that 1 liter of water equals 1 kilogram of water. So whenever I say the mass of water occupied in the cylinder correlated to the mass of the gas occupying the cylinder. So in the United Kingdom, regarding nitric oxide is 0.65. So this is if 100 kilogram occupies the cylinder, we ought to fill it only to 65% of it. I hope that I didn't see the 15 minutes I told you before. Wassalamu alaikum wa rahmatullah wa barakatuh.